Right now in the California desert, a dish the size of a 10-story building is pointed at empty sky. Listening. It is waiting for a whisper. And the whisper is coming from 24 billion kilometers away. Voyager 1 is still talking to us. A spacecraft launched in 1977, built with technology older than the internet, older than the personal computer, is drifting through interstellar space right now, sending home a signal on just 23 watts of power. That is less than a refrigerator light bulb. And NASA is still receiving it. The signal travels at the speed of light. Nothing moves faster, and it still takes more than 22 hours to arrive. One way. That means when an engineer in Pasadena sends a command to Voyager 1, they wait 44 hours for the round trip. Nearly 2 full days for a conversation with a machine they launched 47 years ago. The engineers who built Voyager were working with slide rules and punch cards. The spacecraft's onboard computer holds 69 kilobytes of memory. Your phone holds more in a single photograph. And yet the signal arrives. Faint, yes, buried in noise. Stretched thin across the void. But coherent, readable, real. As Carl Sagan wrote in 1978, the Voyagers are destined eternally to wander the Milky Way. He was right. Voyager 1 crossed out of our solar system entirely in August 2012. Confirmed by NASA Jet Propulsion Laboratory through plasma wave measurements. But the fact that it is still out there is only the beginning of the story. The real question is how. How does a 1970s machine, running on a dying power source, transmit coherent data across interstellar space? And what exactly is it saying from a place no human object has ever been before? Voyager 1 weighs 722 kilograms. That is the weight of a grand piano. Engineers at JPL assembled it by hand in the mid-1970s, fitting it together in a sterile clean room in Pasadena, California. Every component was chosen to survive decades of cold, radiation and silence. John Cassani, the project manager who oversaw its construction, insisted on redundant systems throughout. Backups for the backups. That decision, made in 1975, is a large reason the spacecraft still functions today. Power comes from 3 cylinders packed with plutonium-238. No solar panels work this far from the sun. The plutonium decays naturally, releasing heat, and that heat is converted directly into electricity. Simple, durable, brilliant. But here is the problem. Each year, those generators lose 4 watts of output. Susan Dodd, Voyager's current project manager at JPL, put it plainly in a 2017 interview with Scientific American. We have 22 watts to play with, and that's continuously going down. Less power than a refrigerator light bulb, dwindling across interstellar space. So how does Voyager actually talk? It carries a 7-meter dish, about the width of a large dining table, aimed precisely back at Earth. From that dish, a 23-watt transmitter fires a radio signal. 23 watts, your average kitchen light bulb uses more. That signal travels at the speed of light for over 22 hours before it reaches Earth. By then, it is spread across billions of miles of space. When it finally arrives, it is 1 billion times weaker than the signal your home Wi-Fi router produces. NASA Deep Space Network catches it anyway. Enormous dish antennas, the largest stretching 70 meters across, scattered across California, Spain, and Australia, working in relay so Earth's rotation never breaks contact. But if the signal is that impossibly faint, how do those antennas actually separate it from the constant hiss of the universe itself? 3 giant dishes, 3 different continents. 1 impossibly faint signal. That is the architecture keeping Voyager 1 inside human reach. NASA Deep Space Network operates antenna complexes in Goldstone, California, Madrid, Spain, and Canberra. Australia, the spacing is deliberate. As Earth rotates every 24 hours, at least one of those 3 sites always has a clear line of sight to Voyager's position in the sky. The planet itself becomes the relay system. Each dish is enormous. Goldstone's primary antenna stretches 70 meters across, the width of a football field tipped on its end. These are not passive receivers sitting quietly in the desert. Engineers schedule time on them like operating rooms, allocating hours-long blocks to a single spacecraft, because hours are what it takes. Here is why Voyager's signal arrives at Earth carrying about 160 bits of data per second, according to NASA Deep Space Network published specifications. That is slower than a fax machine from 1985. And the raw signal, when it first hits the dish, is buried completely inside background noise from the cosmos. It is invisible to the electronics, technically speaking. But here is where it gets strange. Engineers use a technique called coherent integration, which simply means listening to the same whisper for hours, then mathematically stacking every repetition on top of itself. The noise being random cancels out. The signal being consistent builds. Like pressing your ear harder and harder against a wall until a murmur becomes a voice. The result is extraordinary. A 23-watt transmitter, 24 billion kilometers away, becomes readable. Scientists still find that remarkable. Susan Dodd, Voyager's project manager at JPL, has noted that no other operational spacecraft demands this level of sustained, careful listening. The process runs around the clock. Technicians monitor accumulating data through night shifts, watching signal quality climb slowly above the noise floor over hours. It works consistently across interstellar space, which raises the obvious next question. Once all that engineering effort extracts the signal, what is Voyager actually saying? Sources: NASA Deep Space Network Capabilities and Services. NASA JPL Voyager Mission Status Reports. 2023, Susan Dodd, Scientific American. November 2017. What is Voyager 1 actually doing out there? On August 25, 2012, the spacecraft crossed the heliopause. That's the exact boundary where the sun's wind of charged particles finally gives out and true interstellar space begins. Scientists had theorized about that boundary for decades. Voyager crossed it silently, automatically, without ceremony. The instruments still worked. What they measured had never been measured before by anything humanity built. Plasma density, magnetic field direction, cosmic ray flux, the rain of high-energy particles streaming in from distant, dying stars, according to Donald Gurnett and his team at the University of Iowa. Writing in Science in 2013, the plasma outside the heliopause was 40 times denser than anything inside it. 40 times, a number that rewrote textbooks. And that is not even the strangest part. In October 2023, Voyager 1 stopped sending readable data entirely. Not a weak signal, not static. Coherent-sounding transmissions carrying pure nonsense. From 24 billion kilometers away. Something had gone wrong inside a computer no human hand could ever touch. Engineers at JPL spent months diagnosing the problem through a 45-hour round-trip conversation. Send a command, wait nearly 2 days for the reply. Adjust, wait again. In April 2024, NASA confirmed the cause, a single corrupted memory chip in the flight data system. They rerouted the code around the damaged section. Software surgery performed across interstellar space. The fix worked, but the clock is still running. Voyager's plutonium power source loses 4 watts every year. Linda Spilker, the current project scientist at JPL, has said engineers will need to shut off the last functioning science instrument before 2030. One instrument, then silence. Which raises the question that the final chapter has to answer. What does it mean that we built something that outlasted our ability to fully understand what it's telling us? Tonight, somewhere over the Mojave Desert, a signal is arriving. It left a spacecraft 24 billion kilometers away. It traveled for more than 22 hours at the speed of light, crossing a distance so vast it makes the solar system feel like a backyard. And it landed quietly in a dish pointed at empty sky, the same dish that opened this story. That signal is not engineering alone. It is the farthest message humanity has ever received. Voyager 1 is the only object ever made by human hands that has crossed into interstellar space and reported back. One spacecraft built in a California clean room in the 1970s by engineers with slide rules and early computers. Still talking, still heard. Think about what that required. 50 years of decisions that had to be exactly right. The trajectory Charles Colhais calculated. The redundant systems John Cassani insisted on. The engineers in 2024 who spent weeks diagnosing a single corrupted memory chip from 24 billion kilometers away and fixed it. Every one of those decisions held. But here is the part that lingers. One day, probably in the 2030s, Voyager's power will finally drop too low. The transmitter will go silent. The conversation will end, and then something quiet and extraordinary will happen. The spacecraft will simply keep going. No signal, no instruction, just momentum, carrying it deeper into the galaxy for billions of years. The golden record will still be attached. Diagrams of human figures, sounds of Earth. A message with no intended recipient, drifting through 400 billion stars. Carl Sagan once wrote that the Voyagers are destined eternally to wander the Milky Way. He was right, we just didn't fully feel it until now. A machine the size of a grand piano, running on less power than a refrigerator light bulb, has become humanity's only emissary to the stars. And it is still out there, still moving, a bottle thrown into an ocean with no shore. If moments like this make the universe feel bigger and stranger, subscribe, there's a new one every day.